G'day Bifrosters, here's something a little different. It's code, it's a bag of pythons. And this code does this. And I'm going to take you through it. Why? I hear you ask, faintly in the background. Well, this is the introduction to visual coding. So visual coding has two components, visible things and coding. Here is the coding. So I'm going to take you through the code and then we'll recreate the same thing in Bifröst. And hopefully we'll be able to tie the two things together. So I'll have the editor open at the same time and we'll go through the code as well. I'm not going to rewrite the code because we'll be here all day while I look things up. Which is the secret to coding, is basically stack, exchange, copy and paste. That's how you learn to code. That's how I learned to code. That's how a lot of people I know learn to code. But technically, let's be honest, this is a script. This is an algorithm. So what this does is it puts a random point in a sphere of radius r. Alright, so Mel has this automatically. It's the Sphrand command. This is what you've got to do in Python to get the same result. Okay. But it's an algorithm I had on hand, and it's an algorithm that puts a point in a sphere of a certain radius. Okay, so let's delete this, and I'll go through the code line by line for you. So when you're coding, especially in Python, and we're going to talk about Python because although Mel is super useful, Python is even more useful because Python lets you write code for Houdini and Blender and Maya. I have no idea about Cinema 4D, but I would not be surprised. What else? Godot is based on Python if you're into game engines. I'm not sure about Unity, but I've seen Unity code and it's not that dissimilar to Python. Python's really handy. It's used a lot. It's not the fastest language around, but it's also, it kind of makes up for that for being everywhere and being able to do everything in it. I've written games in it. Not very good games, not games that anybody has seen, but I have written games in it. If you really want to see them, tough luck because I'm embarrassed for them. Nah, drop me a line, I'll send you something. This is Python, and the first thing we do in Python is we import the libraries that we want to use. So in this case, I'm importing the Maya commands as CMDS, which means wherever you see CMDS further down in the code, that's a Python Maya command. That's a Maya command. So this command, object exists, that's a Maya command. Polycube, that's a Maya command. Move, parent, they're all Maya commands. You can prove that by going over here and see it turns blue. If I just type, it doesn't turn blue. When it turns blue, it's a command. It's a Mel command, it's also a Python command. So we're importing the Maya commands. We're importing NumPy, which is a math engine for Python. And when you see this, import Maya CMDS as CMDS, that's the name of the library, Maya.cmds, Maya.commands, as what you want to refer to it as. So it's import the library as that. Import the NumPy library as that. And then when you don't see as, it just means we're going to use this to refer to it in the code. So import random, you can see it here, random.uniform, and import math, math.acosine. Okay, so that's our libraries imported. We need those imported before we start coding. This weird little thing, def, what this is a function. So what I'm doing here is I'm writing a function that I can call at any time. So Python takes that, it runs it, sticks it in memory. So whenever you use it further on down, and you can see that we use it here, it becomes a command for me because I've built it here. Now this is the algorithm. This is the algorithm for putting a random point in a sphere. Okay? It starts off with a random point between 0 and 1, a random number between 0 and 1, and another random number between 0 and 1. It then gets an angle, theta, which is this number multiplied by 2 pi, basically. And math.pi is how you get pi in Python. I'm explaining all of this because we're going to do this in Bifröst as well. We're going to rebuild this entire algorithm in Bifröst just by looking at this and copying things over, and you'll be able to see how we do it. Okay, so we have another one. Phi is the arc cosine, math.arccos, of 2 times v there minus 1. So that's the a cosine of that, whatever that random number is. R is our radius. Random.uniform 0, r. Now this looks like it's referring to itself twice, but it's not. This one here is this bringing this in here. I could change this to q. I could change this to q. Let me just check I don't have q somewhere else, because that would get confusing. I have a p but no q. I could change those two to q and it would still work, but r is fine. It's just this is redefining r as a random number between 0 and r that came in, and the cube root of that number. So that's Python speak for the power of, to the power of 1/3. 1.0 over 3.0. So this is a random number between 0 and this radius we bring in to the power of 1/3, which is the same as a cube root. Now here is how we calculate our actual coordinates. So these will become our vectors. Radius multiplied by the sine of phi, which is this guy, the acos, multiplied by the cosine of theta, which is this guy, plus 0.0. Because p up here, for most programming languages, you'll need to declare a variable first. Python, you don't usually. And what I mean by declare a variable is that p is a variable, and by including it up here, and I'm giving you the Cliff's Notes of Python here, there's a lot more to this. The coders in the audience are at this point screaming at the screen, and I really don't blame them. I'm a very, very bad man, at least when it comes to Python. But in this case, p is a variable, and we're declaring it to be an empty NumPy array. We're just making sure that if you don't tell it what it is to start with, which is what this p equals means. See, r doesn't have an equals, but p does. If you don't tell it what it is to start with, that it starts off as a NumPy array that has 3 things in it, all of those things are 0. This is essentially declaring the variable for a vector. Now, if you don't know about vectors, let me know. Please let me know, and I'll go one step further back, fire up Khan Academy, and we'll talk about vectors and the length of them, how to multiply them, and all of that kind of thing. But for now, just take it as read that this is how you do a vector in Python. Alright, you need to use NumPy or something that lets you, another good one is Euclid, if you can get that library. But NumPy is a good one. Any NumPy array is treated as a vector. Right, back to where we were. So your x component is radius multiplied by the sine of phi multiplied by the cosine of theta plus whatever you've put in here. In this case, it's plus 0, so it's just really just this. The y component of the vector is radius multiplied by the sine of phi multiplied by the sine of theta. And between those two, you're making a circle. It's getting to look kind of spherical on here. And then the z component is the radius multiplied by the math cosine of phi plus whatever this is. So all of these are usually 0 unless you actually specify them to be something else. This is a good way to do an offset. Basically, that's why I've put this in here. If you leave this as it is, it'll generate a sphere around 0 of a certain radius. If you put something in here, so when you run the command, you put in 2 arguments. So this is an argument, and this is an argument, and it's a variable. I know it gets confusing, but if you bear with me, I'll try and smooth it out. But if we put something into this argument, it will act as an array, and you can then build a random point in a sphere around a point you specify. All right? So that is an algorithm. Well, technically, that is the algorithm. And an algorithm is really just a set of commands that tells the computer how to do things. And what this set of commands tells it to do is put a point, give me the vector of a point in a sphere of this radius, anywhere in that sphere, randomly. Which is why we've got the 3 random calls here. Alright, so give me a point that's inside a sphere of radius r randomly. That's what this algorithm does, and it does it really well. Okay, so we haven't even started the script yet. That's the algorithm. That's the engine. That's the thing that does everything. Here's where we have to do things to get Maya to play well, okay? So this is declaring an empty array of points. Now, if you've used Bifröst at all, you would have heard arrays thrown around a lot. An array is a list of things. It's just a list of things. That's it. It's a shopping list. It's the number of TV channels you have. It's the number of streaming services you subscribe to. It's the number of movies you've seen in the last year. All of them are arrays. It's the number of toes you have. Anything that can be put in a list in any order is an array. And Bifröst has them. It has an array of points. When you wanted to, say, deform the points on an object, it has an array of particles that you can do things to. So that's the basic explanation of array, and this creates an empty one. And also what this does is if I run this twice, this will clear the array that already exists. Yes, I know coders, that's not strictly true, but shush, this is for people who don't know how to code yet, okay? Next up, we have a loop. Loops are important. What this does in Python is it gives you all of the numbers between 0 and 999. So it's the range of numbers in 1,000. So what this is saying is for each number in the range of 0 to 999. So these two lines literally loop 1,000 times. Does this, does that, does this, does that, does this, does that, until it's done 1,000 times. Bifröst also has a for each, and we will also be having a look at that today. So this is where it generates the points. All right, I can show you this because I don't have to run this all at once. I can run this bit, and you see nothing happens. Nothing happens at all. But something's happened up here in your script editor. It shows you it's run. So it's imported all the libraries, and it's put that into memory as a command. Okay. So we can start off by going, give me an empty array of points. And the lovely thing about coding in Maya is that I can see what's in that just by highlighting it and running the program. And it's saying, points, those two brackets tell me it's an array. The fact that there's nothing in those brackets tells me that that array is empty. Let's run these two lines. So remember, this is the loop that loops 1,000 times, and this is our command. And this is a radius that I tested earlier. So what this is going to do is go round and round and round and round 1,000 times. Every time it goes around, it's going to run that command. And what this is, there's our empty array. Remember, points, p&ts is empty. This is an array command, points.append, which basically says put whatever is in these brackets next in the array. So the first time round, it puts in the first result. The second time round puts in the second result. Third time round, third result. And so on and so forth up to 1,000, or whatever number you put in here. I could make this 50, I could make it 50,000. If I made it 50,000, it would run slower. It would take a fairly long time for Maya to actually execute all of this. So we have a loop that is generating a bunch of random points. Let's run that. Let's run it. Has it worked? Well, let's check our points. Yep, that looks like it works. Each one of those is a NumPy array. You can tell because it's got array and then bracket and square brackets. Right there. Remember when it was empty, it looked like this? This is what it looks like when there are things in it. And I can test to see how long that array is by, if I just come down here, we'll just do a little bit of length. So this is another Python command. Len will give you the length of an array, 1,000. So my loop has worked 1,000 times, and it's put 1,000 things in that array. I can check that another way by going the name of the array, and then any number between 0 and 1,000. Let's try 680. There we go. The number that is 685th in the array is minus 2.4, minus 3.0, and minus 4.3. That is a random point inside a sphere of radius 244, because that's what my algorithm does. Okay, we have our points. We can check it, because I'm quite paranoid when I code. I'm fully convinced that data disappears into the vague wastelands of my CPU and overcluttered hard drives and RAM. Moving on to the next bit, what this does, this is just a little bit of Maya housekeeping to keep things tidy. Because I'm going to make 1,000 cubes, and I'm going to make 1,000 cubes in a sphere in a radius of, in this case, 244. 1,000 cubes in my outliner would make for a very horribly long outliner. So what this is doing is it's saying, if not, this object exists cubes. So this part's Python, if not. So if that was just if object exists cubes, it would mean do whatever comes after this colon if this object exists, but if not says if this object does not exist, do that. And what that, so object exists cubes, let's check it. You can just run part of the line. False. There is nothing called cubes in the outliner right now. Not even if I turn off DAG objects only. There is nothing in there called cubes. And that's what this is doing. This is saying, is there anything in Maya right now called cubes? If the object exists, you see these, this means it's a string. It's looking for the name of the object in the outliner. So if object exists, cubes. If it doesn't exist, do this. If it does exist, which is what the else is, so if not, else. If not this exists, else do this. Yeah? So that's saying if this already exists, make it our group. But right now, if it doesn't exist, make a group that is empty with the name of cubes. This is how Maya scripting works. And you can literally see Maya do its stuff. Apart from the 1000 warnings about parenting things in the underworld. You can see here, undo. You can see here, polycube. This is all Maya's notation. So this is me right, you're looking at me write a script here. And that's my startup. So you can just see the script editor gives you this, the history tab up here, gives you everything Maya's doing under the hood. It's a huge part of how I learned to script in Maya. I've been given a job where I have to put 300 buildings on a grid, and I really don't want to do it manually. How do I do it automatically? How do I do it with a loop? That's what drove me to do it. Except it wasn't 300 buildings. It was about 8 million particles in RealFlow in 2012, 2011, something like that. So I figured that there's got to be an easier way, and Python is that easier way. All right, enough of my stories. Let's run this. So if this doesn't exist, make it. If it does exist, use it. You can see in the outliner we now have an empty group called cubes. So it's doing exactly what it says. Don't need that now. Now the last thing is we're actually going to create the cubes. So right up until now we haven't created the cubes. We've created an array of points where we're going to put the cubes, yeah? But we haven't created the cubes. This next loop for each in points is very similar to for each in range, except instead of for each in the range of 1000, for each in points. So for each one in here. And you don't have to call it each. I just do because I've got some bad habits, right? You could call this each vec in points. And we'll just change everything that refers to each down here and make sure that it's all hooked up and we're good. So for each vec in points, this is creating a new variable and it's putting this polycube in it. This is a Maya command, cmds, which we imported at the top. Polycube makes a cube of width 0.2, height 0.2, depth 0.2, and because I've given it no other options, it will make it at the origin. So it'll make it at 0, 0, 0, which is what I want, because the next command is to move that cube. Move it to these 3 points, which are inside points. It's part of the loop. So for this, let's run it through in our brains. The first one is 0.0 in points. It's the first thing in points. Everything counts from 0. So let's have a look at what that is. The first value in 0 is this. So the first time through this loop, it's going to make a point cube. It's going to move it in the x to that point, in the y to that point, in the z to that point. And it's going to do it absolutely. So an absolute move means it makes the translates that. It doesn't just add those to the translates that are already there. And then the last thing before it does, before it goes back to the beginning of the loop, is it parents PC, which is where we put our point cube. This variable is now referring to this point cube, polycube, not point cube. So this variable is now referring to this cube we created. It's just saying parent that to that group. So put it in there. It's the easiest way to think about it. And this is the bit that actually makes the sphere. There you go. So we have 30 lines of code here, going from importing the libraries, building the command, building an array, looping through a arbitrary number, 1000 in this case, running that command, making a group to hold our results if it doesn't exist. If it does, don't worry about it. And then actually building our cubes and putting them in the group. You can open this out and you have a whole bunch of cubes. In fact, you have 1,000 of them. Great. That's how you do it in Python. Why did I show you this? Well, I showed you this because this is non-visual coding. Invisible coding? Invisual coding? Who knows? But this is what you need to do to create this. Okay? We're going to refer back to this now because we're going to recreate this in Bifröst. So I'm going to show you how to take non-visual coding and bring it into a visual coding environment and do exactly the same thing. Okay? Pretend you didn't see that. So just to make things a little bit sort of easier to see as we go, what I'm going to do is I'm going to take this cube and I'm going to template it. So they'll just sit there and they'll be grey in the background and I can't select them and everything's happy. Okay? So the very first thing we want to do is make sure we don't have anything coming in or going out. This is our input and output in our visual coding system. Let's get a little bit more realistic. So we can now refer to what we did. For a start, we don't need to do any of that because Bifröst has a random. It knows what a vector is. Python doesn't. It knows what an array is. It's already got all of this stuff. It knows how to do sines and cosines and that kind of stuff. It knows how to do a cube root. That's all cool. So we don't need any of the libraries straight away. Great. Let's build our algorithm first. Okay. So to do that, I'm going to make a compound. And we're going to call it Sphrand. And what you have to think about, just like when you're non-visual coding, is what is coming into your algorithm and what is going out of it. Back in the script editor, what is coming in is the radius. So the radius you want the sphere of, the sphere as. And what's coming out is a bunch of points. So it's a vector array is what's coming out. Well, it's not. I lie. A single point is coming out. So let's do this. I mean, this is, I would probably jazz this up when I was doing it in Bifröst. In fact, I did. But let's do this exactly as this does. So what goes in is the radius of the sphere. What comes out is a single point within that sphere. And that's what this is, the algorithm to do it. Okay? So we have an input. We need an input. That input needs to be a float. So it's a radius. Floats here, floats good. Let's switch this over to name display so we can see what we're doing, and we'll call this radius in. And until you're used to visual coding, it's good to label things and name things obsessively. If you've ever opened one of my compounds, you will see that I do that all of the time. So right now we have an output. We have an input. Let's keep the naming up so that when we're deep inside here, we know what this is because it's written right there. I think I'll get us a bit more real estate here. And I'll do the same with the script editor. Like that. Yeah, you knew I wasn't going to hit it. You just knew that. Although that's pretty damn close now. Okay. So we're inside our Sphrand compound now. All we've got coming in is a radius. And we need to do some things to that radius. Before we do that, we need to generate a couple of random numbers. Now, Python does it with the random library, random.uniform 0, 1 just means make me a random number between 0 and 1. So let's do that. Let's have a random value, like this, between 0 and 1, and it's a float. Great. So we'll call this u, because the variable is named u. This generates u. What I'm going to be really careful to do here is I'm going to make sure these two have different seeds, because otherwise it'll give you the same number. So let's pick a random number, 24. And all I need to do is copy and paste that. Change it to V, and we can test that. Random value 0.22262. That's the random value we're getting for U. Let's have a look for V. Yep, they're different. Which is weird because they have the same seed. Okay. I'll just prove myself wrong all day. On with the algorithm. So that's those two lines knocked out. We've done that. Sometimes, oopsie daisy, we're not in Bifröst. Sometimes a good thing to do here is group those into a compound, call them variables, get inside here, and let's just get out. Drop those in there. We'll just rename this to U and rename this to V. And now, then you've got your random variables just coming out of here. And you can go back in and add new ones when you need to, which we will in a minute. So this is just a way of keeping things tidy. You don't need it. You can have U and V all over the place. You can have all the stuff you want. This is going to get kind of messy, so I'm trying to keep it all in one place so that it's visual. You guys are visually able to see it real quick. What's the next thing we need to do? We need to start and make theta. So let's make theta. We can make U times 2 times pi. Yeah? Now, what I'm going to do is do it in here. Because I can, and it keeps things tidy. So let's make theta. Let's go, we need to multiply. And we need to multiply this value, which is U, by pi, which is why we didn't have to import the math library. And then we need to multiply that by 2. So this is 2 times pi times this random value, and that's theta. We come back and have a look at theta. There it is. U times 2 times pi. Perfect. So that can go out here and be called theta. So you can see how we are pretty much mirroring the code as much as we can. Right? So that's theta done. There's pi, and there's 2, so that becomes 2 pi. What's next? Math.a cosine 2 times v minus 1. All right. So in the brackets, basically what we need to do is we need to do this first and then do that to it because of the law of order in mathematics. And that applies again. We need to do this first, 2 times v minus 1. So 2 times v happens first and then 1 is taken away from it. So we'll go back to here. We already have a 2, and we already have a v. So we need to multiply. And that was 2 multiplied by v. And then let's just get this a little easier to read. 2 multiplied by v. And then we subtract. So this part here means we've done what's inside the brackets. So what we have to do to all of that is ACOS, which arc cosine, there it is. Bifröst has done that confusing thing again. Okay, so that is random value v up here. Comes down, gets multiplied by 2, has 1 subtracted from it, and then that whole thing is run through a cosine, and that becomes phi. Now these are called theta and phi and u and v and r because the tutorial I found on how to code it used those names. I first coded this. Actually, I think I first coded this maybe around 2010. Well, not even. Nah, probably more like 2015, actually. Because I needed a Sphrand for some impact stuff, and there it was. So we jump back up a bit. We've got u, v, theta, and pi. Cool. Great. What's next? Now this is where we need to get our input and do stuff to it. R equals random.uniform, all of this stuff. Now, if you wanted to say, take a bit of code over to Bifröst so you could reference it, you could do a couple of things. You could come here, create a backdrop. Yeah, take it out of the backdrop and paste that bit of code in the backdrop if you wanted to. There it is. That's just sitting there pretending to be a backdrop name, and it's all good. You could do that. It's very small. I think you could also put it into the name of an object like that, except it's going to strip out everything that the names don't like. So let's not do that. So we'll just have to squint and zoom in. We can do a couple of things to help with readability, like make it black so it's a lot easier to see from further away, depending on your eyesight. But just a note, if you wanted to get something in, because you know I need a random of this and that and blah 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 blah. So this is where we need to do stuff with our radius, right? So let's just jump up. Let's give ourselves a radius. Oh, we did 12. What? Yeah, no, red 12's good. Let's use 12. 12's good. So we'll go back in here, which means I now want to put this radius into my variables compound. So I've got the radius coming in. I also want to take this guy and drop him in here so I can see what I'm doing. So here's our radius coming in. So the R coming out needs to be random number between 0 and that radius. Well, we know how to do the random numbers. We've got them here. All right, so that just becomes the maximum of that random number. And I don't trust the seed thing. I'm going to change it. I'm going to change it for all of these. I don't know why I'm using multiples of 12. I just am. So the radius coming into the max of a random number gives us everything up until this point. And then we just need to take the cube root of that. Does Bifröst have a cube root? Sure does. Now we could do it the same way. We could do it as a power. We could do this as a power of 0.333 recurring. That does exactly the same thing as that. But we've got a node for it, let's use it. So we take the cube root. And let's go look at our reference. So R coming out equals random uniform between 0 and R coming in to the power of 1/3, or the cube root. So we have our other variable now. We have our R going out. Let's rename that. Still not doing much right now. We're just building our variables. But if you come back to the script editor, we're all the way to here. We're about to start generating our points. I'm going to want those because those are good things to have. Now I'm about to test something. So we're done making our variables, basically. Delete that for now and everything will complain, but that's all right. We're done. We've made our variables. Now we need to actually run it through the algorithm. So I'm going to drop a backdrop without anything selected, like that. Paste all that in there. See, yeah, it's holding that nicely. Just make it a bit bigger so we can see it, and I'll make it black so it's easier to read. So this is how we actually make our points. So let's just jump ahead. Let's be a little non-linear for now. Right away, I'm not going to worry about this position coming in. All right, that was just for the script I wrote. It was for a very specific thing. Bifröst makes it super easy for you to just add an offset to all of these points at the same time with a for each loop, which we'll do once we get there. But for now, I'm going to ignore that. I'm going to treat all of those as 0, so you can just wipe them off the equation, because anything plus 0 is itself. So we didn't actually need to put u and v out, because we don't use them out here. We use phi, there it is. We use theta, there it is. And we use radius, there it is. So I can come back in here, and I can quite happily break those two connections and delete those ports. Because u and v, the random numbers u and v, these two here, they are for generating stuff in here. They're for generating other variables. So I literally don't need to see them outside of this compound. Okay, this rough intro to visual coding, some of this is just how I do it. You can do it differently. There are 1,000 ways to do this, and none of them are wrong. Some of them are slower than others, and I'm not for a moment saying that I know how to super optimize things. You want to get on the Slack channel and talk to some of the absolute magicians on there if you want to find out that stuff. I don't know that stuff. I'm still learning this too. But what I do know is how to translate an algorithm into visual coding. And that's what I'm showing you. So just bear in mind, this is my way. If you can find a better way, hell, do it. and then send me how you do it so I can learn too. That'd be great. Thank you so much. Let's build our points and stop waffling. So let's make x first. X equals r multiplied by the sine of phi. So first off is we go sine of phi. There we go. That's the sine of phi there. And multiplied by the cosine of theta. So let's get the cosine of theta. Yeah, that's that done too. Let's throw it out a multiply node. And again, rules of mathematics apply. R multiplied by sine of phi multiplied by the cosine of theta. They're all multiplications. They all happen interchangeably. You can multiply them in any order you like. I'm going to keep it to the same order as the algorithm so that people don't get horribly confused and hurt. But sine first, cosine second. Not even. I even got that wrong. Oh, not even, bro. Radius multiplied by sine multiplied by cosine. This is our x point coming out. So we've got our first point in the vector. That's it. Let's do the y. Again, it's r multiplied by the sine of phi. Well, we've already done the sine of phi. That's up there. I saw the sine, and it opened up my mind. So let's put it in multiply down. I hate it when it does that. I don't know why it does that. I hate it so much. Burning passion. R multiplied by the sine of phi, because we've already done it once, multiplied by the sine of theta. Now we don't have the sine of theta. We have the cosine of theta, but we don't have the sine. So let's drop that in. There's the sine of theta. This is sounding like some obscure religious thing at this point with all these signs and stuff, but that's okay. It kind of is. Let's just double check our work. R multiplied by the sine of phi multiplied by the sine of theta. So R multiplied by the sine of phi multiplied by the sine of theta. All good. Let's name some stuff. Yeah. Naming stuff's good. So I know what's going on. I can see it. It's visual after all. Last but not least is the z component, which is r multiplied by the cosine of phi. So another multiply node. Drop r into it. We don't have the cosine of phi. We have the sine, but not the cosine. So let's do the cosine. Drop that into it. And that's that done. X, y, and z. Now we just need to make a value to turn them into a vector. To do that, that value needs to be a vector. Shut up. Output. And then we can literally just plug x into x, y into y, z into z, and that's the output of our algorithm. So we've done exactly what we said we'd do. We have a radius coming in, we have a vector value coming out. It's a position vector, so I'll call it position. Alright, so that is our output coming out. You can see it's not an array, it's a single value in, it's a single value out. Okay, that's the value it's come out with. 80201774883656976. That is our random number. Okay, doesn't look much like this yet, but it will. But it will. What mesh have I done here? That's really interesting. I don't know what I plugged into Bifröst. Possibly a cube. It doesn't matter. We're going to make our own anyway. Delete that now. And we can delete that now too. So how do we actually do this 1,000 times? Well, the same way we did it in Python. For each in range, run that command. Okay? So we're not going to do an each in range. Well, we kind of are, but we don't do it that way in visual coding. We're going to put down a for each loop. Ignore that you saw a for each in range in there. All right. What I'm going to do is I'm going to copy this whole thing. So the whole compound, wherever we're getting one, I'm going to put it inside this loop. Like that. So this is looking for a radius in. I need to bring the radius into this loop. So that's just a matter of grabbing the radius and putting it into the loop. Cool. Hook it up. So our radius is coming in now. Now watch what happens when I hook this to the output. You see these 3 dots in a triangle? That means it's a port iteration target, which means it might be a single value coming out of here now, but we come out of here and it's an array. And it's an array of this many things. It's an array of 10, and I can prove it to you by going up here. Yeah, no. Yeah, nah, bro. Going up here, you can see array of size 10. Yeah? That's it. Now that's interesting. That's where the seeds come in, I think. I need to change the random seed every time around the array for this to work. At the moment, it's putting out 10 of the same values. Maybe it's not. Hard to tell. There is an easy way to tell. Let's find out. But let me just go back to what I was doing first. We wanted 1,000 cubes. 1,000 cubes we shall have. The size just jumped to 1,000. So right now we have 1,000 positions, which means in terms of the coding, we're at this point. We have our points array, and it has 1,000 things in it. Okay, we don't need to worry about this. We don't need to worry about this, or moving it, or parenting it. We're done as far as the code is concerned, because Bifröst handles this differently. Let's go and do it in Bifröst so we can see. Okay, so we have a radius in. It's 12. There's our single command where we were building it. We can unhook that and can delete that port. Here's a loop that does it 1,000 times. What I need to do is I need to put a cube on each of those points. The easiest way to do that is to do it in here. Get an array of cubes coming out. Actually, that's not the easiest way to do it. The easiest way to do it is create instance. Create instances. So now we get into the more Bifröst specific stuff, all right? Create instance is what's a points object. This is a collection of numbers. It's not points yet. Let's make it points. In fact, I don't even need to. No, I don't need to construct points. I don't even need to create instances. I have a node that will show us what's going on. So I've made a point object here. Let's get our instances back in case, or we probably do for the cubes, but I could cheat. I'm going to take this guy and I'm going to put down one of my nodes called point display. What point display does is it allows you to put in a whole bunch of points and it'll show them for you. There they are. And you know what? It hasn't worked. All of those values are the same because the seed for the random values doesn't change throughout the loop. So it's generating the values. There's still 1,000 of them. They're just all exactly the same. So to fix that in Bifröst, I need to put my current index into my Sphrand. And what my current index does is it starts at 0 and counts up to 1,000. So every time around the loop, it'll be 0, then 1, then 2, then 3, then 4, then 5, then 6, then whatever. Right? Which in Python is handled by for each in. So this is saying for each thing in here. There happens to be 1,000 things in here. So the first one will be the first one, then the second one, third one, fourth one, blah, 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 blah. Same stuff. All right. Now we have a seed coming in. And we need to go into the variables where we set our random number. Well, several random numbers actually. We need to bring that seed all the way into there. So let's bring it in there. This is going to be use as seed. And remember how I didn't want to set the same seed for everything? And I still don't. I really, really still don't. So what I'm going to do is I'm going to increment. See, we're a little bit different from the Python now. Python just handled this. This part of it. Now you can already see a change, right? Look at that. So I'm going to do this again, except this time I'm going to increment by 2. Just making sure we get different seeds. You can see it starting to work in interesting ways. And then we're going to increment by 3, pop it into there, and suddenly we've worked. Right, they're not cubes yet, and they don't have the same radius, but that's easy enough to change because we're in visual coding now. We're working procedurally. We're thinking with portals. We're doing all of that good stuff. Let's go all the way back up to the top. We'll need to lift this radius up until we're around about the same as the other one. Oh, it's going to be a big one. There we go. Use the same number and it actually works. So we're right now we're outputting spheres, but we can output cubes. There we go, Bifröst cubes. With a default size. So if you know what, I'm going to give these a color so they're a bit easier to distinguish. We are done. We've recreated this exactly the same thing, both in a script and in visual coding. I haven't actually output any cubes. I can if you want, which is where the instances come in, which is real fast, like that. Those are the points we want to put the instance on. Create a mesh cube is what we want to instance, and we can literally just pop that out there. There they are. Our cube is a bit big. And we'll turn that off to avoid some confusion. So basically the filled in cubes are Bifröst and the wireframe cubes are Maya, are Python. It's done. And that's the way to translate an algorithm into visual code. This, believe it or not, is a reasonably simple algorithm. There are simpler ones. Drawing a cube at a certain point is an algorithm. But this was just one that had some meat to it that I thought would be good to have a look at. It's also had the bonus of actually existing before I did this. I've already built it, and I've already built it in Bifröst as well. But essentially what we've done, just to really quickly recap, we had a look at this Python that generated a bunch of cubes in a sphere of a certain radius randomly. Those are random numbers in there. That's them there. Little pink things. Really nice. This is the algorithm that makes it. Rather, that the def and return is the Python command that creates a command for me. We make an empty array. We put 1,000 things in that array by looping through the range of 1,000 and running the command inside it. We then append the result of that command to this array, make a group to hold everything, make a cube at the origin with these dimensions, move it to whatever the point is in the array 1,000 times, and then parent it into that group. And that's what's made this. On the other side, we did pretty much exactly the same thing. We started with a radius. We made the algorithm here. Inside the algorithm, we took our radius in. We used a compound to keep our variables tidy. And this is where we made all of our variables. So this is the radius coming through here. This is u and v, and all the calculations that are needed to make them. We just output them to the output of the compound. These trigonometry functions, sine phi, cos theta, cos phi, let's name it. These these generate our points by multiplication. So that's our y, and that's our z. And so this whole thing here is literally that whole array there, minus the offset stuff. But I explained why I wasn't using that. So that algorithm in Bifröst looks like this. Now we had to go back and do some stuff with the seed to make sure that our random numbers weren't just kicking out. We had to do that in a loop. This generated 1 point fine. We found that when we repeated it 1,000 times, which is here, that we needed to use the index of the loop as a random seed to generate a different number in our variables every single time. And those are the blue lines you can see there, and the increments. So that's the one big difference that comes with the visual coding, is that I had to go and actually manually make the seeds. But once I did, everything else is the same. This is the same algorithm as both that and that. Okay, the for each loop is essentially there. or maybe there. It's there actually. It's that one, I believe. For it's here. And no, it's running the command and outputting. So literally this here, this loop, corresponds to that. So you loop through 1,000 times and run your algorithm every time. We don't even do this in Bifröst. First thing we did is we used a point array just to show the positions of the points, and then we actually made some instances of cubes in the right places. So the pink ones are the Python and the grey ones are the Bifröst. All right, so that's what I'm going to call an introduction to visual coding. I'm comparing non-visual coding, Python coding, to visual coding. I'm showing you how we're doing exactly the same thing in both methods. I really hope it helps. If you'd like me to do something a bit simpler, this is very much aimed at people who don't know how to code and who are just starting on visual coding. I've run through it really fast, and I possibly haven't explained it properly, but it's a start. You know where to find me if you're watching this video, because my contacts are all on the YouTube. You already just leave me a comment. I'll read it. I read all of them. Even the weird ones that send me the links that you shouldn't look at work. I read the comments. So leave me a comment if you'd like me to take you through something. If you'd like me to explain something better, just let me know and I'll do that. All right. Thank you very much.